Thank you very much. Now we have Renan Almeida from the Institute of Physics of the Federal University of Rio Grande do Sul, talking about percolation in the ordinary kinetics of twisted nematic phases.
Hi, good afternoon. So today I want to tell you how percolation theory can be applied to the ordering kinetics of certain types of liquid crystals. This presentation, I think it's divided in 3 parts. I consider a nematic phase, which is a fluid with orientational order. And this order can be designed using the boundaries of a container. For instance, for a container of parallel plates with orthogonal order between them, there are 2 ways of matching these boundary conditions. Either you go with left-hand twist nematic conformations, or you go with right-hand twist nematic conformations. That's how a two-state system can be made. And under microscopy, these 2 states are easily distinguished. Now, consider a bubble, its interface, and the opposite phase surrounding it. When I apply a high enough voltage in the material, the interface gets darker and quickly expand. By turning off the voltage, we see that these are actually disorder regions made of entangled, string-like topological defects. So if I turn on the voltage and wait time enough, these defects fully dominate the material. And that's an instance of a non-equilibrium, nematic, disordered state. By suddenly removing the field from this disordered state, we get an ordering process, very, very like that of the simple kinetic Ising model with ferromagnetic interactions. In fact, the dynamics can be quantified by Ising-like variables. For such a family of processes, it is known that the typical domain size grows diffusively in time. Well, this is well respected in the experimental data. Other quantities which are expected to be universal, such as correlation functions and the Moster scaling forms, are also in harmony with the experimental results. So the message here in this part is we have a very clean experimental system with simple Ising-like dynamics. But much more on these, for much more details on this parallel, please check the paper. So now I want to tell you how percolation theory comes into the scene. Starting with a mosaic of domains, we can attribute to each domain a unique color to get this beautiful panel. And please pay attention that the largest green domain crosses over the image from the left to the right, from the bottom to the top in this case. By looking at different samples during the ordering, we realize that a domain may cross the rectangle in 3 different manners. A domain can cross the rectangle along with its vertical direction only, along both horizontal and vertical directions, or along the horizontal direction only. The question is, what are the probabilities associated to each one of those crossing types? Well, for Bernoulli percolation process in 2 dimensions, at the critical point, these crossing probabilities are exactly known. They were initially derived under assumption of conformal scaling variance, and later on, rigorously, mathematically speaking, proved for certain models. The results can be read in terms of the rectangle's aspect ratio, R, and in terms of hypergeometric functions. There are results for the vertical crossing probability, horizontal one, and dual spanning configurations. So in this plot, I show the 3 exact solutions for the percolation model. And now I will compare it with data extracted from the non-equilibrium dynamics at or from a given time. And surprisingly, when we do that, we see an agreement for the vertical crossing probability simultaneously with the agreement for the dual spanning configurations and horizontal crossing probability. That's beautiful. The famous-Cardis formula is just a linear combination of two fundamental crossing probabilities. And there is also verified experimentally. So the message of this part is that the non-equilibrium dynamics, geometric aspects of non-equilibrium dynamics can be described by the simple percolation theory. Now I turn to the evolution of Hall enclosed area. Let me first define what is a Hall. A domain may contain inner domains. The Hall is just the external boundary of a domain. And the Hall enclosed area, it's like this. By starting from a mosaic of the generated by the percolation model at the critical point and letting the cluster evolve in time with curvature-driven dynamics, very clever people have proposed an exact formula for the number density of Hall enclosed area A as a function of time for a family of ordering kinetics. This formula has a single parameter lambda, and it was verified in simulations of the kinetic Ising model. However, experimental evidence for it is still unclear. Here I show a log-log plot of the number density of Hall enclosed area versus area at several times in the liquid crystal setup. The curves shift down as time elapses because small domains shrink and disappear faster than larger ones. And interesting, in my experimental setup, I know what is the value of this constant. So I can compare the experimental data, or I can test the theory with no fitting procedures. So when I insert lambda into this equation, these are the outcomes, and they are in very nice agreement with the measurements. This agreement continues if you look at the master scaling form and compare it with the corresponding universal curve. So in general, the area of an object is scaled with its perimeter to the power alpha, and alpha equals 2 for regular structures, but it's much smaller for fractal objects. So let's take a look at what happens in these structures during the ordering kinetics. If you do this plot, the area of the hull versus its perimeter, we observed a crossover from regular to irregular shapes, and that occurs for several times. So what's happening here is that at the beginning of the ordering, so you have a binary system, well mixed at the initial conditions, and they are led to evolve. What happens is that at the initial times, very early times, the system approaches to the random percolation critical point, creates fractal structures, and later on, correlations which are growing and building the domains are destroying the fractal carpet. So that's why you see a crossover from regular to irregular structures. So in summary, we have seen that certain ordering process may be modeled by the simple percolation model at the critical point, plus a certain type of interface dynamics. When you do that, theoreticians have proposed a set of exact equations for non-equilibrium systems. And these equations, these formulas are here experimentally confirmed for the first time. The results are on arXiv, and I hope to be published very soon in a good journal. So as an outlook, I wonder myself if other properties of percolation model, such as its invariance under conformal transformations, are also preserved at experimental level. Furthermore, recent literature shows a lot of evidence that this connection to percolation seems to be very robust for other types of ordering process. So it may be possible to appear also in the phase separation of colloidal system and certain biological matter. I think these questions are interesting from an interesting perspective. Thank you for your attention.
Thank you very much. I have a question. Do you have any sort of idea if any of these features could be translated to systems of conserved quantities instead of Allen-Kahn, but Kahn-Hillier kind of models?
Yes, there are studies simulating the Eisen model, but with conserved quantities. And these models face separation, and people have found a very similar scenario. Starting from a well-mixed initial condition, the system initially approached to the Rundle critical percolation point. You have the fractal structures, and you can derive a set of formula for the evolution of geometric figures in non-equilibrium systems. So I think this is very robust. And people are now understanding this is also happens for systems with quench disorders, long-range interactions, conserved dynamics. So I think this is a very general thing. Yeah, maybe.
Okay, so let's think again.
Thank you.